You have guided notes. You should have 5A and then 5B1 and 5B2. You have have three sets of guided notes for this chapter. So there's some terms that you need to know. There's how to explain, and as we go through some of this, these will be explained. Otherwise, they are explained in your guided notes. And so your guided notes should be able to tell you some of the answers to these questions. All right, we're going to do one of each type of these questions, and then you have pages of examples. So we're going to do 2D velocity example, one of those, one of acceleration, one horizontal projection, and one projection at an angle. And then you'll see that the corresponding pages after that kind of go along with those types of problems. So you can go back to your example if you need to. All right, so the first example that we're going to do together is determining two-dimensional velocity. So this is going to feel very familiar to kind of what we've done before, except it's asking how to correct. So you have to first figure out where it's being pushed and then kind of do the opposite. So it's a little bit different than last chapter, but it's going to feel very much the same. So it tells us that it is flying due east at 120 kilometers per hour. It encounters a strong crosswind blowing south at 40 kilometers per hour. How does it need to correct its direction? What's nice about this one is we don't have any angles. If they had said northeast, that's a 45-degree angle, right? That we would have had to do cosine and sine for our x and y. But for this, we know that it is trying to go east, which is just 120 in my x position. South in my y position looks like that. Had it been anything else, we would have done sine and cosine to calculate those x's and y's. We would have added them to see his displacement vectors. And now we're going to look at direction. Direction is always going to be that inverse tangent. Remember, you can ignore this for right now. We will use what we have to figure out how it's blowing. So it is blowing this particular helicopter 18.4 degrees. Remember, it always gives me a reference angle. If I look back at my x's and y's, a positive x, negative y tells me fourth quadrant in that coordinate plane, which is in directionally, it is blowing me south of east, right? So to correct, I need to do the opposite. If I'm trying to go east, that's what I'm trying to do, then I need to correct it by going 18.4 degrees north of east. We are just doing the opposite of how it's moving me to get me back to where I want to go. So the next thing we have is acceleration. Acceleration is, you're going to have to determine its velocity vector, and then you're going to have to take that velocity divided by time to figure out its acceleration, all right? So this is beginning and ending, so you may want to start at the ending and so that you write it down correctly and you subtract correctly. You'll also notice that it's asking for acceleration, and it gives you velocity. But I always want acceleration in specific units. How do I want my acceleration on these? I want it in meters per second squared. So if you have to make a mental note of that, you may want to on your test. You may want to write a physical note. But you'll notice in this particular problem, they gave everything to me in kilometers per hour. So when I get my final velocity of this guy, it's going to be in kilometers per hour. So before I divide by my time, I am going to have to do a conversion. You can wait till the end to do that conversion, but you are going to have to do that conversion. So it starts out flying east at 180 kilometers per hour. After 30 seconds, it changes course to northeast and increases its speed to 250 kilometers per hour. So I'm actually going to start with that ending one. My ending velocity is at an angle. Northeast is a perfect 45-degree angle in the first quadrant. All right, so I'm going to keep them both positive, but I am going to do its 250 kilometers times the cosine of 45, and I'm going to do 250 kilometers times the sine of 45. Had it said like southeast, then that would mean that my y would have ended up negative and my x would stay positive, right? Southwest, those are both negative, south and west. So think about these are always 45s when they give it to you like this, northeast, southwest, etc. But what quadrant you're in may determine those positives and negatives. I'm going to subtract from that where I started from. I started exactly 180 kilometers per hour east, which means this, I don't have to do any angular to calculate that. When I put those in, I got about 176.8 or so. When it's all said and done and you do your subtraction, you should end up around here. All right. That is my x and y movement of this vector. I need the magnitude of this vector to figure out how I am moving. So I'm going to do that x squared plus my y squared there. And I actually I think I ended up with approximately what the two were actually, which makes sense because it didn't move it that much. That is in kilometers per hour, and it is velocity, not acceleration. All right. Remember, we're doing displacement velocity, not just beginning speed versus ending speed. We're talking about displacing. So he was going a direction, he's going a different direction. If he had been going the same direction, we would have just done, ending velocity minus beginning velocity and not worried about direction. We need to convert. So remember the conversion from kilometers per hour to meters per second. My kilometers would be on the bottom, which means my meters would be on the top. My hours would be on the top, which means my seconds would be on the bottom. So you always end up dividing by 3.6, right? And you get 49.1 meters per second. That is still just my velocity. To get my acceleration, I have to take that and I have to divide it by how long it took me to do that. And they tell me that in the problem. In the problem, it took me 30 seconds to do that. I have 3 significant digits. So when I get this to 3 significant digits, I get approximately 1.64 meters per second squared. So for horizontal projections, this is where you really only have a horizontal velocity. It is not being chunked up or down, just straight across. So anytime you see horizontal velocity, it is shot horizontally. That means, like our video that we saw of them shooting the bullet, they shot it parallel to the ground. They weren't pointing up or down. Okay, when you see that word horizontal. When you see just a drop like this and a plane is flying, you're going to assume that the plane is not flying up or down, or they would have given you some sort of angular measure there, right? So it says during a relief mission, a cargo plane is flying at a constant speed of 180 kilometers per hour and an altitude of 500 meters. The pilot needs to drop food supplies to a refugee camp. How far in advance of the camp should the pilot release the supplies for them to land accurately? So again, I want to point out some units. They've given me kilometers per hour, but then meters here. So again, before you start this process, you want to make sure you're doing your conversions. So my initial velocity that they gave me is my horizontal velocity. The plane is moving horizontally. They've given it to me in kilometers per hour. So I do want to make that conversion to meters per second. Same exact conversion. 1,000 over 3,600, divide by 3.6, you should get 50 meters per second. They've given me an initial altitude. That is going to be my initial y value of 500 meters. Now remember, if you look at your formulas, you're going to see all this additional information. It's going to say, your final height that's going to be your initial height plus your initial velocity times time plus 1/2 gravity times squared. But we don't have an initial a velocity for y, and my final position for y is 0. So the reason we do it the way we do it is because my change in y ends up being my final y, 0, minus my initial y. So I end up having this negative 500 over here, because that's what I'm actually doing. I'm taking that 0 where it's going to land and subtracting the initial over. And then for these, the only thing affecting how long it takes for it to fall is really gravity. And so here we're solving for times squared. It's going to be the square root of 1,000 divided by that 9.81. So that tells me really the time of it dropping. How far in advance indicates that they want me to give them a horizontal distance to drop, right? And so if I need to figure out my horizontal distance to drop, I am going to take that 10 seconds and multiply it by how quickly it was traveling horizontally to begin with. So I'm going to take the 10.1 seconds that I get there to get my change in x horizontally. I'm going to say 10.1 seconds times 50 meters per second. And I will get that it needs to be about 505 meters ahead of that drop spot when it actually drops it. Now again, 3, we have 3 significant digits. That 0 is significant and is in between 2 significant digits, so that's a significant digit there as well. So you do have 3 significant digits there. Projections at an angle. In a physics demonstration, a ball is launched from the edge of a cliff at an angle of 25 degrees above the horizontal with an initial speed of 45 kilometers per hour. If the cliff is 80 meters high, how far horizontally does the ball travel before hitting the ground below? So much information. All right. So they've given us an initial speed, but this is now affecting a vertical speed and a horizontal speed because they have launched it at an angle. All right. They didn't just shove it off the cliff. That would be just horizontal. They actually chunked it off the cliff, right? Which means they shot it up at an angle. They threw it up an angle. However they launched this, they launched it at an angle, not just horizontally. So when I calculate my velocities, I have to consider a horizontal velocity, which is going to be that initial velocity multiplied by the cosine of the angle at which it was launched. And I have an initial vertical velocity, same 45, but now I'm going to do sine of that guy. Now, when I do this, I get 40.8, but I am in kilometers per hour here. Pay attention throughout the entire thing. You may or may not have to convert. In this case, you do. So I'm going to do that conversion. Why do I know I need to do that conversion? Well, all of my formulas that deal with time deal with gravity, which our gravity is in meters per second squared, which means I need meters per second to plug it into an equation with gravity. They gave me the height in meters, right? So I know I'm going to do a meter conversion. I know I'm meters per second because of gravity, all right? Because gravity is meters per second squared. We don't want to mix units. So when I do those conversions, I get approximately, with 3 significant digits, something around there for those 2. Now I need a couple of things. If I need to know how far it's going to go horizontally, I have to know how long it's going to be going that far, right? So I have to go to time. The only thing that affects the time is your initial horizontal velocity and your initial height. Those are the 2 things that affect how long this guy's in the air, all right? So I'm going to use that little, hey, I'm going to be on the ground. I need my initial plus my velocity, if I could do that, times how long I'm in the air, plus that 1/2 gravity times squared. And remember, over and over when you do this, this creates a quadratic. We're going to write this quadratic in standard form. So I'm going to rewrite this. I'm going to say I want the squared piece of it first. Then I want this piece, and I have already calculated my initial vertical velocity. That is 5.28. And they gave me my initial height. I am at 80 meters above the cliff. That is going to equal my final height. Well, if I hit the ground, my final height is 0. And that is a beautiful quadratic that we can use the quadratic formula for. And so when you plug that into the calculator to get that quadratic formula, negative b plus, remember you just have to worry about the minus, square root of b squared minus 4ac over 2a, you should get about 4.61 seconds. All right, that's how long this guy is in the air after it's launched. However, they want to know how far horizontally this guy has traveled. So if I want to know how far horizontally, my change in x is going to be my initial x, which we are going to assume is 0. We're starting at 0 here because it says how far from. And it is just going to be my velocity of x, which is the 11.3 meters per second, multiplied by the time that it is traveling that fast, 4.61 seconds. And I get that it travels 52.1 meters horizontally. Now, a couple things I want to point out. For something like this, where you are elevated, you're not going to be able to do maximum height and just divide by 2. So I typically won't give you a maximum height for something like this. But if I'm on the ground and I'm launching it and it hits the ground, remember maximum height happens halfway across, right? To find height, I have to go back to my height equation. This is finding height. This is finding horizontal. Like x-axis, how far across I moved versus how high I moved. So you may have to use your time and go back to your x, velocity times time, to see how far x moved. Or if it wants something like maximum height, you're going to cut that time in half, assuming it begins on the ground and ends on the ground, but then go back to your y position formula that you had. So you would go back to that negative 4.905 x squared plus velocity times time to see how high it actually went. So think about what it's asking. Is it asking how far across or how high it has traveled?